Hello everyone and welcome back to the second video. I have tried to fix the audio problem this time. If the problem still persists, do let me know in the comments. So, in this video, I am going to talk about my processing workflow and I will also talk about the way astronomical data are stored. That is, I am going to talk about FITS file. I will give you how a FITS file is stored. Then I will show you how to open up a FITS file, and then I will show you what are the standard things that we usually do with our FITS file. Okay, so without any further ado, let's dive in. Now, first of all, I am going to talk about my workflow. Now, everybody prefers a different workflow. As far as I know, professional astronomers prefer to use Python for their work. Now, image processors usually use softwares like PixInsight or Photoshop to get their work done. Some of us also use MATLAB. Everyone has its own workflow, and I prefer, or I rather, choose all of the three methods. I use Python in my workflow. I use softwares like Photoshop, PixInsight in my workflow. Along with it, I use MATLAB. Now, a software could never be your restriction. A software could never stop you to analyze the data. Suppose you don't have MATLAB, then you can do all the things in Python. Suppose you don't have Photoshop, you can do the same thing with Photoshop in GIMP. So, a software is never your restriction. Now, why do we prefer to use Python? Python gives a lot of flexibility about the way we can visualize the data and then further process it. Now, in my channel, I'm going to talk about all the methods. Most of the upcoming videos will deal with Python and using Photoshop and PixInsight. Along with it, I will also use some software. So, if you guys are not using a Linux computer, I would suggest you to do one because for analyzing X-ray astronomical data or for UV astronomical data, most of the softwares are written for Linux or either macOS. So I would suggest either you run up a virtual machine or you can dual boot. We'll go into those topics in future videos. So let's dive in to FITS format. Now, what does FITS stand for? FITS stands for Flexible Image Transport System. A FITS file consists of a lot of headers. A FITS file usually is composed of header units, and different header units have its own functionality. Okay, so if I have a FITS file, it has headers, or rather, header units. Okay, now what are header units? Header units are basically some integrated structure within a file. A header unit can either contain the data of the observations in text format. By text format, I mean like when is the observation is taken, with which filter the observation has been taken, who is the PI of the observation, what is the target, what is the coordinate of the observation, etc. And it also contains imaging data. That is the data that we are gathering. Let's say we are observing some galaxy or getting some imaging data. It is also stored into a header unit. I will show you in depth about the header units in this video. Before we dive in, let's just look in what an image really is. An image is basically a numbers. Images are basically numbers. Why do I call them numbers? All the images that we see, like the images that you're capturing from your phone, they're actually black and white. They are captured in different wavelengths, different colors to them are assigned, and then after combining them, you get a colorful image. Or before combining them, they are all black and white. Now, an image has generally three types of resolution: spatial resolution, spectral resolution, and differential resolution. Okay, spatial resolution deals with the size of the image m cross n. Let's say an image is typically a full HD image like 1920 by 1080 images. It is basically the spatial resolution of the image. Spectral resolution, the spectral frequency at which the image has been observed. Let's say a telescope is making observations in optical wavelength, so it will be optical. Some are observing in near infrared, some are observing in X-ray wavelength. So these are the spectral resolution. Now, the last thing is the differential resolution. Differential resolution basically talks about between how many different shades of gray an telescopic camera can distinguish. Okay, I will show you the picture over here in a bit. You all have heard about 2-bit image, 4-bit image, 18-bit image, 16-bit image, and 32-bit image. But we all may have doubted like what do these bits mean? And these means a 2-bit image means the camera can distinguish between 4 different levels of gray. A 4-bit image means 16 different levels of gray. 18-bit image means 256 levels of gray. Usually our laptop screen or our phone screen is an 8-bit image. It's either 8-bit or 16-bit. Okay. 32-bit images that we capture are from very sophisticated camera. These are usually these are usually giant telescope like Hubble Space Telescope, or you have heard about ESO, the Hawkeye instrument, or the very large telescope. The camera over there can captures at this resolution, at 32-bit resolution. They captures at 32-bit resolutions also. Okay. Now, and what do I mean by different shades of gray? Also, this is what a 1-bit image means it is either black or either white. A 2-bit image means 4 different shades of gray. A 3-bit image means 8 different shades of gray. 4 different images. A 4-bit image means 16 shades of gray, and so on, so on, so on. From this, you can easily identify you can easily recognize how precise the camera is onboard Hubble Space Telescope because it captures a 32-bit and it differentiates between 16.7 million levels. Okay, well let's say I have an 8-bit image and each pixel has its own value. We call them pixel values. It can be one, let's say it's an 8-bit image, it's 120, it could be 30 over here, 40, 50, 37, etc. Okay, like the entire pixel value is given in the image. Now, one thing that you need to remember, the lowest value is absolute black and the highest value is absolute white. If you know this, you won't have any problems. Okay, so I will show you first on Python like how do you load up a FITS file. Okay, now I have already written the code, so you don't need to worry about it. If you want to give them a try, I have this code up and you can run them. You can run them and check it yourself. All the steps are given here. I will explain in this video about the header files and the fits files. So I'm not going to explain all this stuff. I will make future videos on using Python as a very important tool in astronomy. Okay, so in those videos I will going to explain all these things. I I will load up an SDSS test data of M101 Galaxy. Okay, and I have just used this command to give me the different header units contained in this fits file. Okay, there is one primary header unit, one image header unit, one bin table header unit, another bin table header unit. Now, how do we recognize which is the image header unit? And this from here, 2048 by 1489. Okay, this is typically our primary header unit. Okay, since this is the data from SDSS, the first header unit is the image header unit, the dimensions, because the image cannot be one dimensional. It can be one dimensional only if it is a spectral file, but it's no. We know it is a target. We have observed it, so we can easily identify with it and see it's written float 32. This means it is a 32-bit image. Now primary, it will indicate this is our header unit. Now, if we load up some data from the Hubble Space Telescope, then we see the primary header unit is not our header unit. There, the image header unit is our image header unit. Also, there will be like if the file contains raw data or contains some calibration data also, then also there will be two different image unit extra, and those will be calibration header unit. What are calibration? I will talk about that in a later video. I will show you like a data from Hubble which contains these three different header units. Okay. Now, going back to this. Now, what I have did, I want to analyze my primary header unit, that is my image header unit. So I have copied it, and now I have used this command to load up the header. You might be thinking, what is this? This is not an image. But no, every header unit contains some text associated with it. As I said, it gives you the details of the target, like when it has been observed. Okay, when it has been observed, the focusing precision over here, the date of observation, the time of observation, etc. Okay, we can easily analyze this. See, if I run this command, this gives me the name of the telescope. Okay, Python makes it lot easier to analyze a fits file because of this functionality only. Because you don't need to go through the entire fits header to recognize which filter it is or which when who has observed it. You can like easily do it with just a command. Okay, I see here the filter is green. Okay, now I'm going to talk about these, the bits per pixel. Okay, this means this is a 32-bit image. N-axis N-axis means the number of axes in bits in this. Okay, it's 2. But why, like you might be thinking, like, isn't it obvious that an image or header file should contain only 2 axes? But no. Sophisticated telescopes like Chandra Extra Observatory captures the data in 3D. There, the number of axes is 3. Even from ground-based telescopes, three-dimensional observations are possible. And why 3D? Because you may be thinking, we cannot map it out in 3D over there. That would be like very difficult. Yes, we could not map it. But then why is 3D? Because let's say you're observing a pulsar and you want to study the variability of a pulsar over a time. Let's say over 8 days. Now, there are two ways to do that. You can either go for a continuous observation. Okay, continuous observation and break that into subparts, or you can make discrete observations after sometimes, let's say you're observing a target and you're breaking the observations into like say 3 hours long, 3 hours, 3 hours, 3 hours. Okay, so that makes a problem. If we have, let's say, if we break down the observation into 3 hours each for one day, there are 8 observations, and for 8 days it will be 64 observations. Okay, and to write the code or to analyze 64 different observations is a lot difficult than analyzing a single observation. And there comes the functionality of 3D fits file. In 3D fits file, all the observations are stored within a single fits file, therefore 3 dimensional. Okay, let's show you. And the image that the way the image is stored over there is this. These are my two axes, and let's say this is the data from first 3 hours of observation. Then along the you can visualize it as the z-axis, and along the z-axis the next 3 hours of data is also stored. In similar manner, all the observations are stored in 3 dimensional file. So you can make a quick animation of all those 64 observations and then check where is your pulsar variability. Okay, you might have seen a video in Wikipedia about the variability of the crab pulsar or the Vela pulsar. They are all done in this manner. Okay, going over here. Now, I will talk more about the 3D data in the end. Now, let's just go into the image part. Okay, now if I want to load the image of the data that I just captured over here, HTML over here, so I will load it, and as you can see, it's black. Or like most of the fits file comes to us like this. You may think it as useless, but no, this is not at all useless. It contains a lot of data. But then why the heck it is black? Because the data is normalized. Okay, the data that we get is a normalized data. We are not using the entire dynamic range, and also we have not applied any stretch. Now I will stretch. You might have heard of this word if you have looked up the internet about the processes in image processing, and this is a very essential step. If I just plot the histogram of the data over here, you would see just only one. And by this histogram, this is just a frequency histogram. Let's say you have this image. Let's say you have this image, and the over in a histogram, what it's basically doing is, let's say I'm counting the number of 20 that is appearing in the image. Let's say 20 appears twice. Let's say 30 appears for this. So this is what a frequency histogram is. Okay. Now we can see that all the pixels in the image has the same value. But why it is happening? This should not be the case, right? Because if all the pixels have same value, then how could we even differentiate between what's there in the image? And then there comes the stretching. It may looks like this is the histogram of the entire range, right? But if we can zoom in over here, we see like there will be small spikes over there, because you know that these numbers that we're seeing over here, see, as I have told you, this is all our numbers, and see, these numbers are very small. So we know normalization means mapping our data from the entire dynamic range from entire dynamic range to 0 and 1. And see, these numbers are extremely small. Okay, how could we even or I differentiate between these? So it just appears as a peak. There are fine variability over here, but our eyes could not differentiate between those variability. And then we need stretching. Now, for stretching, there are a lot of different softwares. Okay, we could use how image DS9, we could use Python, or we could use Fits Liberator. Now, I prefer to use how image DS9 and Python because they give you a lot of control over what you can tweak. Okay, let me just open up the data. As I have told you, there will be fine detail, but in those small area we cannot differentiate. This might look like a random piece of white dots, but no. And then I will stretch the data and see all of a sudden the data comes in. This has already been present there. What I just did is I have just stretched the data. Okay, I will talk about stretching now. What is basically a stretching is? Yes, as I have showed you, let's say I have my histogram like this, somewhat like this. It's very small area. Okay, now first of all, I will tell you a bit about histogram. The left side and the right side. The left side means the darker part, the right side means the brighter part, and the area in the middle tells about the middle part, like which is neither very bright, neither very light, neither very dim. Okay. Let's say I have the histogram like this, all of the pixels are in darker part. Now, if I could somehow distribute or I could somehow change the value of the pixel such that my histogram becomes like this. Okay, this is my new histogram. Then we see some regions are bright, some regions are dark, some regions are moderately bright. And then we can easily distinguish between the features of the image, and that is what a stretching do. There are there are three type of stretching functions. Okay, there are three type of stretching functions. It can be algebraic stretch, exponential stretch, or trigonometric stretch. Exponential also comes under algebraic stretch. Now, under algebraic stretch, there are three: linear, logarithmic stretch, and exponential stretch, and then the trigonometric stretch. Let's say you have a data. Okay, let's say you have this data only. This I have loaded up over here. If I do a linear stretch, see, nothing happens. Why so? Because we all know about the equation of straight line, right? That is y equals mx plus c. Now, what does a linear stretch do? It takes the value of the pixel, multiplied by some constant, adds some another constant, and outputs a new data. So let's say your pixel value 0.88, and you say you supplied the m to be 2, 2 into 0.8, and let's say your minimum pixel value is 1. So what does it give? 2.76. See, your pixel value just changed from 0.88 to 2.76, and the steps that we do, they are all non-destructive unless you save the file. So don't worry about it. Okay, the stretch is non-destructive unless you save the file. You can easily recover your original data based on the invertibility of the functions. I will talk about the functions in a bit, and then you will realize, yes, you can recover the data because of the invertibility of the functions. I won't dive into too much of mathematics behind this. If you guys want to know more mathematics of stretching, do let me know in the comments, and then I will make another video on that. In this video, we'll just talk about the basic mathematics of stretching. Then we'll go to some demonstrations. In this way, linear stretch usually works. So, how our linear stretch is defined? Okay, let's say you have an 8-bit image. Okay, now an 8-bit image, and it is restricted to this area only. But now you want to map it to the entire range. We can map it. Okay, let's say our maximum and minimum pixel value that we're getting in the original image, let's say it is 68 and say somewhat 14, and this is 0 and 255. Okay, 14, 0 and 255. Now I want to map it over here. So how can I map this data to entire dynamic range using this function? Smax and Smin is basically talks about our required range. This is our current range. Rmax goes to 68, Rmin goes to 14. R, it takes the pixel value. Let's say your pixel value is 20. So R is 20 and Rmin is this 14 and Smin. Why do I need this constant? Because I want to map my data from this portion over here to this portion over here. It should not go below 0, because if it goes below 0, all the data will be black. That is clipping. All the data below 0 will be black and all the data above 255 will be white. Okay, correct me if I'm wrong, if I've written something wrong over here. This is our linear stretching function, and it basically increases each pixel values in a linear manner. Okay, now talking about the logarithmic stretch. This stretch, it is very useful in astronomy, because if we analyze the nature of this function, we see it does not brightens up the darker part. Sorry, it does not brightens up the brighter part very much, but it brightens up the darker part by a significant amount. And the benefit of that is that the part which is already bright, in that area we won't lose much details. You could say we won't lose much details. And in the darker areas, we will recover more details. So, how does this works? This is my output pixel value. This is a parameter that will be supplied by you, and from the name, it is a logarithmic stretch where the base can be specified by you. Now, we can all tweak this parameter in how image.js9 in Python or in fits. And why 1 plus x? 1 plus x because if the pixel value is 0, then the log is not defined. Therefore, to be on the safer side, we write it as log of 1 plus x. And in the same manner, exponential stretch is also defined. Okay. Talking about the trigonometric stretch, we can see over the formula over here. A is the parameter that has been specified by you. X is the input pixel value. For arcsine stretch, this is my output value. X is the input pixel value. A is the parameter specified by you. And this A means sine hyperbolic inverse, or the inverse of sine hyperbolic function. Okay. Don't confuse this A with this A. Okay. The arcsine stretch also behaves in the same fashion as logarithmic stretch. Usually, you won't much notice any difference between logarithmic stretch or arcsine stretch. I would suggest you to compare them both and see if you can find any details or not. So let's go to how image.js9. So here I select scale and I select log, and see we got it over here. Here we can still see the image is pretty dim. We could not distinguish much about the image. So what we do, go to scale parameter and then again tweak with this slider. Now this slider over here, this is the white level control slider, and this is the dark level control slider. Okay, and see as we move this, the image is getting brighter and brighter. Okay, and what do these things doing? they are doing nothing, but they are performing a kind of linear stretch only. They are just increasing the value, they're just increasing the pixel value. Since it is a GUI, you cannot notice it, but here in this here the I will link down this notebook in the description. Here if you run these two cells, you can see you can replicate the same functionality using a linear stretch. So these are basically doing a linear stretch. Okay, see, because the end. And how could we say it is a linear stretch? Because the entire image is getting brighter. The entire image is getting boosted up by some value. Okay, it is getting boosted up by some value. Now, if you play with JSON, you will see a lot of things. Min max. Okay, see, I have told you we can control the log and min max. Now, we want to say like how much data you want to manipulate. How much data you want to manipulate. With that, I mean, let's say, let me just open space over here. Yeah. Let's say this is your histogram, initial histogram. Okay, this is your initial histogram. Interval means with which interval of data you want to play, rather with which interval of data you want to change. Now, if it is a min-max interval, means it will use the entire data from the minimum pixel value to the maximum pixel value. If, see, if it is a 99.5 percent of data, this means that the algorithm will stretch, will not use 0.5% of these values, 0.5% from the terminal side of the histogram. That is, the details from this and this won't be used, and it will map this to here, and it will map this to the outside. So 0 and 255. And let's say the histogram becomes like this. Okay, 0.5% from the terminal of the histogram will be eliminated, or rather say will be clipped. Okay, because anything below 0 becomes 0, anything above 255 becomes 255, and that's what interval means. 99.5% of the data. I will demonstrate it. I am currently using the min-max interval parameter. Okay, min-max interval. Okay, min-max interval means I will use the entire data from the lowest value to the highest value. And if I use 99.5% of the data, see, it has been significantly boosted up. Why? Because 0.5% of the brighter value and 0.5% of the darker value are all flipped to 0. And as you can see, the sliders also move to this one. If my limit is min-max, it is over here. But if I boost it up to 99.5%, over here. So it really depends on you how you want to use the interval. Now, higher is lower is the amount of interval used. Let's say you're using 90% of the interval, the amount with which it will get boosted will be significantly high, because 10% of the data from the terminal side, that is 10% of the dark pixel and 10% of the bright pixels are all white or either all black. So we usually do it at 99.5%, or we use the min-max interval. That's usually works good for us. Okay. I will let you compare the details over here. Now this is a logarithmic stretch. If I do it linearly, see, nothing happens. Even if I stretch it much, see, some details are coming out. Now this is a very hard stretching, because like the loop will very high if we get this data. If it is a logarithmic stretch, it's like this. Okay, and see the parameter is still over here. That's the beauty of the logarithmic stretch. It brightens up the darker part and does not touch it or does not play with the brighter part much. See, we get a lot of details from the bright area. You can see small galaxy popping over here. If I use this power, this comes under exponential stretch. See, it's not much of details, you know. But if you can play with the parameter over here, the exponent, because where is it? Because if you play with the parameter over here, you can pick it. Square root stretch also works sometimes. This is the square root stretch, and see this. Get some details. This is my squared stretch. It usually behaves like square root stretch or the power stretch. You can pick the power. This is usually set to 0. And as I said, the arc sine stretch and the logarithmic stretch. Wait, let me just change this. It's a logarithmic scale, if it is arc sine scale, see the arc sine stretch also behaves in the same manner. Okay, arc sine stretch also works in the same manner as the logarithmic stretch works. Here also the bright areas over here are not blown much. Now logarithmic stretch usually works for most of us, and we can also create custom stretch. Let's say you want to stretch your data first logarithmic, then square root, and then signage. Then I prefer if you use Python, because Python gives you the ability to create composite stretch. Now this is a signage stretch, and same signage stretch is not usually that much helpful over here, but as I've said, the stretch is over here. Now signage stretch usually helps in other digital images, like you're capturing some remote sensing data, then signage stretch usually works good. And these three buttons over here, the min max button I have already told you. The histogram, uh, yeah, this means histogram equalization. Now, why histogram equalization? What do you mean by histogram equalization? Histogram equalization means we are equalizing the histogram. See this histogram over here. Most of the pixels are dark. Some are white and some are in the dark region. But the contrast in this image, it could be very hard. Okay, you cannot distinguish between a lot of the details because most of the pixels are dark. Now, after performing a histogram equalization, we see the graph becomes flattened. What should be an ideal histogram look like? An ideal histogram should look like this. See, this should be flat. And this is what the functionality of histogram equalization is. It tries to equal it tries to equalize the distribution of dark and black pixels, and you get much of the details from the data. Now, histogram equalization usually help with other data like from remote sensing data. It is very useful in those areas because it equalizes the levels and you can easily distinguish between the terrain features over here. Histogram equalization in low contrast image induces noise. See, sorry, yeah. This is a low contrast image because most of the data is situated in the darker region, and so it will induce noise during the stretching. And why the noise is being induced? Because some this is a point. This works and this is a point function. Like because by point function I mean it does work on individual pixels. Okay, in that way it creates some noise. Now, if it has been a good contrast image, let's say the histogram is usually located, the histogram usually spread out over the entire dynamic range. Then the noise won't be induced. I will show you the details, the comparison of histogram in MATLAB. There you can compare the entire data. So I have this code written over here which is yesterday in the morning, and see, I have opened up a file. Let's just wait for the diagram. Wait. This one. This is my histogram equalized data. See, histogram is spread over the entire region. And now, this is the same galaxy or the same fits file. I have just applied some logarithmic stretching over here. So, if you don't believe me, I will show you. See, this is the same image. I have just applied a bit of logarithmic stretching to that file. Okay. So, see, this is my actual histogram. This histogram is not equalized, like, because most of the data, I don't think, why do they look same? Yeah, sorry. Graph and not coming, I made some mistake. See, most of the pixel values are in a darker region, and here the histogram has been equalized. The algorithm has tried to stretch out the histogram so that I can use the entire dynamic range. And as I have talked in the earlier about the normalized data, the image that comes to us is normalized. See, the pixel values are from 0 to 1. Here are also 0 to 1. Now, with the invertibility of function, let's say I have a data equalized, then we can easily revert it back to original data form because of the invertibility of the function. Okay, I will just quickly show you what the function is. This is just a basic math. Like you have all heard about the probability distribution function and cumulative distribution function. It uses that concept only. Okay, so L minus 1 is a range. Okay, n cross m is my spatial distribution. Now, what, and this is the CDF, this is the cumulative distribution function. How does this works? Let's say you have a data. Let's say you have a data. Now, your range is from 0, 1, 2, 3, 4. And the data vary like 22, 344, etc., etc., etc. Here, first we calculate the probability distribution functions or the probability distribution function. What is it? It basically calculates the probability of getting the level 0. Okay. Now, what we need to know is histogram equalization is always works on the same differential resolution. So, if it is an 8-bit image, it will map it to another 8-bit image only. You cannot change from 8-bit image to 16-bit image. PDF. So, let's say the total number of pixels are 1000. So, it's like 0.022, 0.022, etc. We can calculate the same thing from over here. It is 0.344, etc. We calculate the probability distribution over here. This is what I did. Nj over here. Nj, the summation of Nj over M. nm. Now this is constant, I've taken it out from here. Nj, this is a constant. So this calculates the probability distribution of the same value, and then I multiply it. Sorry, before doing that, we first do the CDF, that is the cumulative distribution. Now 0.02 appears like 0.02 times. Sorry, this is a bit mathematical. If you're not interested in this, you can skip. We calculate the CDF and then multiply it by L minus 1 to get the transformed value. The CDF tells about the distribution of, let's say we are talking about this pixel, and it tells what is the probability of getting pixel value 2, a pixel value less than or equal to 2. So what would be this? The probability of getting this plus getting this plus getting this. We all have done this in our 8th standard or in the 9th standard statistics class. Okay, we usually used to calculate the CDF, cumulative distribution. This is the same thing. Okay, and then we need to map the data. To map the data, we have 255. Let's say for 8-bit image, we have 256 range. So 256 minus 1, it gives 255, and then map, and then done. The histogram is equalized over here. See, this is my actual histogram, and this is my mapped histogram. Okay. This is all about histogram equalization. To be very brief about it again, histogram equalization induces noise in low contrast image. But you can try it on MATLAB or you can do it on Python. I didn't use Python in this because it will be very lengthy. So I will quickly show how Fitts liberator also works. So let me just show them. So, and see, I have loaded up in the use of Fitts liberator. It is also been developed in this. Now, as I have told you to use Python. Why Python? Because Python and PS9 are written in a similar fashion. The way we analyze the data is similar to the analysis on Python too. See, uh, this has already been stretched in logarithmic form. Now, if I keep the data linear, see, it's very linear. Now, the data was somewhat over here. Now, if I stretch it, see, the entire image boost up by same constant and then adds up the S-min. Now I have showed you. See, and here we can find all the function linear, arcsine, logarithmic, exponential, and trigonometric. See, arcsine stretch and logarithmic stretch. They are all similar. They almost work similar. See, and there is also not a very significant change in the histogram too. Okay, arcsine, logarithm. So that's all about stretching. Next video I will show you how to do a proper stretching of the data. Also I will talk about how to get the data. In my previous video, or in my first video, I have linked the MAST archive where you can get the data. So if you have any experience with MAST or MAST, you can go get some data over here. It's public over there. I would not prefer, I would rather not suggest to use ESO data. Like if you have any introduction to SQL, structured query language, then you can do that. You can record data using SQL over here, or there is also a GUI based interface over here, but that's not complete. That's not like very efficient over here, but you can try it out. And the last part of the video, I'm going to talk about my Fitts file, which contains multiple header units. Uh, multiple header units. See, these kinds, these, let's say I have a camera. This is camera designed from ESL. Okay, the camera contains 4 observing area. Observing area 1, observing area 2, 3 and 4. Okay, now Each observing area observes its own data of the same target. So let's say I have a very large target. Okay, a single camera could not capture it, but a large camera could capture it like this. And there will be gaps between the camera. Okay, between the camera sensors over here, that we can basically treat them as sensors. Okay, and there the way the fits is structured, it contains the header, the basic header, where the details about the algorithm are stored, and then it contains image header 1, img1, img2, and in a similar manner to img4. Okay, if like in ESA, from ESA data you can easily go up to img32, because some camera sensors are like 32, or basically it's the 32 different parts of a mirror, because the mirror, the the mirror based telescope that they are using has it's segmented using mirrors. We cannot construct a large mirror like that, for like you cannot construct a 8 meter large mirror, but you can easily break them into parts. Okay, that is 64. Now if I just show you over here and see, there are 4 imaging headers, and the primary header unit contains no data at all. Even though SPSS data is observed by ESO, but the way the data is stored is completely different. And it depends on the developer or on the program how they want to store the data. See, and let's say if I want to analyze just one, get the same thing. I got RA, the declination over here, etc., etc. And the wait, I didn't run it. Yeah, sorry. See, I got the bit, I got the n-axis. It is a two-dimensional image, three-dimensional image I will show you later or in the next video. Extension name chip 1, that is that it contains the data from this portion of the camera. This contains the data from this portion of the camera. Observing unit 3 contains the data from this portion of the camera, and observing unit 4 contains the data from this portion of the camera. I will even also load up this on Bits Liberator to show you how it looks. See, it looks like this from image unit 1, plane 1, plane 2. That is this portion over here. For plane 3, that is this portion over here. Sorry, this portion over here, and plane 4, that is this portion over here. This is a very large file. You know why? Uh, and it, because making changes to a single large file is a lot more difficult than making changes to a small file of the same large file, because it gives you a lot of control on the data. Let's say you need to fix some sensor gap or some solar flare, not solar flare, some cosmic waves over there. We can easily fix from one part of the image rather than doing it for the entire image. You can save the computation time over there also. Okay. This has also been this kind of observation is also implemented our observatory also from ISRO. There also the X-ray instrument over there uses the same 4 sensor layout. Okay, and each sensor observes a different area. That's way more versatile, because when each sensor observes a 4 different area around the same target, what it do? It saves time. You don't need to redo the observations of the same region again and again to get data. Okay, and now the ESA header file usually contains a lot of data over here, lot of bits file, because that content they give you the entire details over there. And now this directly comes out from the pipeline. If let's say someone has made some changes over here, it's written over there in the history column. Okay, it's written over there in the history column. So Fitz file also contains a history region also here with could deals with all the changes over here. So let's say your Fitz file you made some changes or you made some calibration over here and you want to send the Fitz file to someone else. Now when that person opens up the Fitz file, he or she will easily know what are the changes that you did. Okay, this one. Where I'm using it, it's also the same thing. Now calculating my histogram in Python sometimes takes a long time, so I won't do it. So thank you for watching. Uh, uh, do let me know in the comments below about what are the things that you want to learn. So in that manner I can prepare my videos. But I have preset plans. I will let you know about my preset plans. So let's say in the next video I will talk about how this video has become much more mathematical, and I think most of you haven't liked it because of that. So don't worry, I will give you a demonstration in the next class, in the next videos. Okay, do let me know like what can I improve more. I hope the sound quality is fixed now. I will try to improve the sound quality in the upcoming videos too to get it more clear and clear. To give you the overview, yeah. So I have talked about this, like stretching functions. So yes, pretty much covered for this video. Just an overview for next video. I will give you demonstrations how to do a proper stretching, how to recover fits file, and how to use the master archive. If time permits, I will also talk about ESO archive too. Okay, so thanks for watching. Have a good day.